Hi everybody, welcome to another edition of Chem 103. I'm sorry that the stream didn't seem to work properly yesterday. Having some technical difficulties, but everything seems to be doing okay at the moment. So I'm going to go back through some of the stuff that I went through yesterday so that you don't have to watch that video where there was a weird time delay. And if you still want to come, we're in room Z351, a few folks here, and we'll be going through some balancing equations and talking about atoms. So what I attempted to do yesterday that didn't quite work is tell you a little bit about how to balance equations. If you want to see these notes, they're in Teams in the class notebook content library. So if I open this up here, the notebook, and when it loads, the content library. All right, that doesn't seem to be loading properly, so we'll go back to that in a minute. All right, so this is a chemical equation, and let me erase some stuff so we can rethink about it now that it seems to be working properly. So where I started with it before, we can leave a few of these things here. Where I started with it before was this idea that if you have a reaction like or an equation like this, a chemical equation like this, we have a problem because if we attempt to account for all the atoms, there's something happening that's not supposed to happen. So if we have hydrogen, like this, HH, and then we have oxygen like this, OO, don't worry too much about the double bond thing. We'll get into that another time. But if that's our two molecules that are undergoing a chemical reaction, and then our product is water, how do we deal with the fact that we have just lost an atom the way that we have it drawn right now? And what I mean by that is the way we have it drawn right now looks like there's two hydrogen atoms on the left, two on the right, two oxygen atoms on the left, and then just one on the right. And that's not correct. That's not what's happening. And the reason we know that is because we can't just have an atom totally disappear. So there's some different possible solutions if you're trying to figure out how to fix that, but only one is correct. So let's look at some of the wrong solutions first. So one wrong solution would be, well, maybe we just add another oxygen atom like that. We can't do that because that would be another product of our reaction. Like if we're showing the equation as describing a reaction, we can't just assume there are other extra products that we didn't think about. So in that case, if we were actually doing this physically in person, you would know if there was some extra thing there. And so there's not some extra thing there, so that's not a solution. Another possibility that some people sometimes try to do is to change the subscripts. So the subscripts are these little numbers. And you can't do that either. Any idea why you can't do that one? Does anybody know what H2O2 is?
Hydrogen.
Is it water? Yeah, it's hydrogen peroxide. Is that the same as water?
No.
It's not. It's very different, right? You would not want to fill your water bottle with hydrogen peroxide. So it's a totally different compound. And that's an important point, that when we are working with chemical equations, we don't want to change the subscripts when we're balancing. Because that would actually change what the compound is. And we don't want to change what the compound is. So then what's the solution here? How do we account for this? The correct solution is to do something called balancing the equation, which means that what the real solution is that hydrogen and oxygen, when they react together, they don't react in a 1-to-1 ratio. So you don't just get one hydrogen molecule reacting with one oxygen molecule. That's what's causing our problems. And so what actually happens instead is we have two hydrogen molecules reacting with one oxygen molecule, and that ends up making two water molecules. So now, if we think of them reacting in this 2-to-1 ratio, you can see that the atoms all work out. We've got 4 hydrogen atoms on the left, 4 on the right, 2 oxygen atoms on the left, 2 on the right. And the way we express that in a chemical equation is by putting a big number out in front, and that's known as the coefficient. So we write a 2 in front of each thing where there's 2 of, and that could be whatever number. If there's not a number written, like by the oxygen here, we're assuming that's 1. So anytime you don't see that number out in front, we assume a 1. Okay, so that's like the basic theory of how to balance an equation, but let's also then look at the mechanics of it. Like, how do you do this? In this case, this one was fairly simple, so maybe you could kind of look at it and figure out how many of each thing needs to change. But in a more complicated reaction, you wouldn't just be able to look at it and figure out, oh, I need 2 of these and 3 of these, because it's going to be more complicated than that. So part of what this sheet helps you to do is kind of go through and think about what has to happen for these things to balance properly, and there's some examples here. So let's go through and do one of the examples. We will do B here. And so Fe3O4 plus CO is FeO plus CO2. So that one, I'm not going to try to do it right there. I'm going to rewrite it so that we can see it a little bit better. So we've got Fe3O4 plus CO. What was the other part? I already forgot. FeO plus CO2. Okay. And I'm going to ignore the other parts that are in there, like the states, those little things in parentheses. That tells you if it's solid, liquid, gas. We don't need to know that to balance it, but those are sometimes in chemical equations. All right, so if you see something like this, you might be able to see right away that it's not balanced because there's 3 iron atoms on the left, that's Fe, and there's 1 on the right. But it's probably not apparent exactly what numbers you need to put in to get it balanced. So here's the actual procedure to actually go through and balance something like this. So first thing you want to do is take an inventory. So account for all the atoms. How many of each atom are there on each side? And we're going to use the arrow as our separation here. So we've got 3 different types of atoms. We've got Fe, which is iron. We've got C, which is carbon. And we've got O, which is oxygen. And then we're going to count up the number on each side. So on the left side, we're going to sum everything together. On the left side, we've got 3 total Fe's. We've got 1 total C, and we've got 5 total O. The 5 total O comes from the 4 from the first compound and the 1 from the second compound. And then on the other side, we've got 1 Fe, 1 C, and 3 O's. With me so far? Good? Okay. So now we need to add coefficients to bring these into balance. And there's not really like a rule for what order you have to do them in, but any atom that's in a bunch of different compounds, it's best to save until the end. So for instance, oxygen is in every single compound in this equation. So if we try to balance that one first, it's going to throw us off, and we're going to have to end up changing some stuff later because the left side has 5, the right side has 3. So we know we need more on the right side, but we don't know where those more are supposed to come from. Are we supposed to add more FeO, or are we supposed to add more CO2? We don't know. So let's start with the Fe first, and then that will hopefully lead us to the right numbers for the oxygen. So we have 3 Fe on the left and 1 on the right. And we want 3 total on the right. All right, so we will put a 3 in front of here as a coefficient. And then this is important, you have to update the numbers because that 3 doesn't only affect Fe, it also affects the O. So we now have 3 Fe's total on the right. We haven't changed the number of carbons, but we have changed the number of oxygens. So now we have 3 plus 2 is 5. Oh, and so that's it. So now our equation is balanced. I didn't realize that would be quite so simple, but we just needed to change that one number, and now everything's come into balance. If that wasn't true, then we would keep going and try something else. So let's try another one that will take a little bit more work than that. Let's go with C4H10 plus O2 gives CO2 and H2O. Okay, this is combustion of butane. C4H10 is butane, the same stuff that's in lighters. And we're going to go through the exact same procedure. So we write down our 3 atoms that are in this equation, CH and O, and we add up how many of each one there is. So there's 4 on the left and 1 on the right. For hydrogen, there's 10 on the left and 2 on the right. For oxygen, there's 2 on the left and 3 on the right. 3 total, because we're adding up all the compounds. So we're using the subscripts here. As we add coefficients, we're going to have to multiply the coefficient by the subscript to get the total number of atoms. All right, so let's start balancing. Again, we have oxygen in a lot of different compounds, 3 out of the 4, so we're going to save that one until last. It doesn't matter if we start with carbon or hydrogen. Either one of those should work fine. We'll start with carbon because I wrote it down first, but it doesn't matter. So we got 4 on the left, so what kind of coefficient do you want to put on the right?
4 on the CO2.
Yeah, we want to put a 4 here also, so that we now have 4 there. And then we're going to update our numbers here. So this means we now have 4 carbons, and we've changed the number of oxygens. So 4 times 2 is 8, plus 1 is 9. So instead of 3 oxygens, we now have 9 oxygens. All right, let's do the hydrogen. We've got 10 on the left, 2 on the right. So what number do we want to put here in front of the H to make sure we get 10 hydrogens?
5.
5? We're going to see that? Okay, good. And again, we're going to update our numbers. So we now have 10 on the right, and our oxygens are now 8 plus 5 is 13. Okay, so all that's left is oxygen. We have to bring that into balance. So we've got 2 on the left, 13 on the right. So what are we going to put next to the oxygen to make 13? There's a problem here, right?
Yeah.
What's the problem?
It's an odd number.
It's an odd number. So if we're using whole number coefficients, we can't put anything there that would work. Because if we put 6, we get 12. If we put 7, we get 14. So what's the solution? Any ideas?
Double everything?
Yeah, let's double everything. So if you run into this problem, you can double everything, and then the numbers will work out. So let me show you what that looks like. We put a 2 here. We'll leave the oxygen alone for now because we know we have to put something there. We haven't put anything there yet. But instead of 4 here, we'll put 8. And then instead of 5 here, we'll put 10. Redraw that plus sign. And the reason to double everything like that is then we don't have to worry about the carbon and the hydrogen again, because we know the numbers are different, but they're going to be in balance. So let's check our numbers again. We've got 8 carbon and 20 hydrogen, and we also doubled the right side, so 8 and 20. But now, instead of 13 oxygen, we have 26, and that's a nice even number. So now we can go back over on that left side and put a 13 here and have our 26 oxygens, and that thing is now in balance. So to make that look nice, we would probably erase these other ones, right, and then just have our 8 CO2 and 10 H2O. Okay. So there's lots of practice for this in your lab from either Monday or today. You can go through and work on balancing the equations from lab. You can do them during lab today if you have lab today, or you can go back and do them if you did lab on Monday. That's a good way to practice. The link I posted in the chat, I don't have right now here. Yesterday, the link I posted yesterday, I don't have right now, but I will post it in Teams as another way of checking yourself. It's kind of like an online chemical equations quiz, so once you feel comfortable with it, you can give that a try. As you're working through this document, please skip a couple things. Here, yeah, I put this in yesterday, but we'll check it again. Please skip 2 and 3. Those deal with moles, and we haven't done that yet. We're doing this in a little bit different order this time. So don't worry about anything that talks about moles. And then because this comes from a whole class, it also has this assignment that says read the assigned pages in your text and work the assigned problems, so you don't have to do that, as you know. All right, any questions about balancing equations? Online, you're going to send me a message on Teams. Let me check real quick and make sure that nobody is saying anything in the chat here. Okay, we look good. Okay, then let's move on to atoms. There's a similar activity for looking at atomic structure. And this one, I'm not going to tell you the answers to as much because I think you can work through this. What's going on here, this is always a weird thing to look at when you first pull it up, but what's going on here is just some models of some atoms. So they've used some different colored circles to represent different particles in atoms, and they've given you a key about them. So they've said protons are these ones here, then you've got neutrons and then electrons. It doesn't really tell you what those things are yet, and that's okay. Then you've got these boxes that are named with atom names like hydrogen, carbon, magnesium. They have these little symbols in the upper right-hand corner, and they have these AMU numbers below, and they contain various numbers of these dots. And then underneath the boxes, there is a description of what they are. So you've got some things being called isotopes, nucleus. Again, it's not defining these things. It's not defining any of this. It's just presenting them. And that's the whole point of this type of activity, is rather than just give you definitions and things, if you work through it, you will discover the definitions on your own, and they will stay in your brain longer than if you just read it. So when it asks you these types of questions, the questions are almost like ridiculously easy. And so for that reason, people often overthink them. But the first one just says here, look at the schematic diagram for carbon. What do all three carbon atoms and ions have in common? So it literally just wants you to go look at these boxes that are above here and say, okay, here's what I see in common about these three atoms. I see, you know, do they have the same letters? Do they have the same numbers? Do they have the same numbers of things? So like, what is the same? And if you go through them, we can do this one together, you'll see that there's only really two things that are the same about these. One is that they're all called carbon and all have a C for a symbol. And the second is that they all have 6 protons. But everything else about them is different. They have different numbers of neutrons, they have different numbers of electrons, they have different AMU numbers. So the only thing we can say for sure is the same is that number of protons. And so that's what we would write here. What do all three carbon atoms and ions have in common? We would say names and C, and we would say number of protons. Okay. And then it says, what do all hydrogen atoms and ions have in common? So you go back and do the same thing for hydrogen. Then it says magnesium atoms and ions. You go back and do the same thing. And hopefully you'll discover a pattern there. So let's do those together. We go back up to the hydrogen ones. And we see the same pattern as the carbon. They've got the same names, they've got the same letter symbols, and they've got the same number of protons. Each of those hydrogens has 1. If we look down at magnesium, again, we see that same thing. Names and symbols are the same, numbers of protons are the same. So, using the magic of technology, I can maybe copy this. Can I copy it, actually? I don't know how that works on here. Nope, I'm just totally messing it up. Okay. If I was on a computer, I could copy it. Oh no, now it won't let me even look at it. Okay. Well, I guess I shouldn't have done that. So same and same. Okay. So then it's asking you to use those three ideas, look at a periodic table, considering your answers to these questions 1, 2, and 3, what is the significance of the atomic number above each element in the periodic table? So if we look at the periodic table, I don't have one right here on screen, but pull one up in your book, or look, if you're in the classroom, you can see. If we look at carbon and hydrogen and magnesium on the periodic table, we see that they all have an atomic number that is equal to the number of protons that we just described. Right? So that must tell us that the atomic number is equal to the number of protons. So then we can extend that a little bit. How many protons are in all chlorine atoms? How do you think you could find that? Yeah, we could look at the periodic table, find the atomic number, 17. So then could chlorine atoms exist with 18 protons? What do you think? Probably not, right? Why not?
It has to be the same.
Yeah, because what would 18 protons be? It would be the next one over, which is Ar, argon. Right. So that is actually what ends up defining an atom, is how many protons it is. That's how atoms are different from each other. So that's the idea of this activity. This one's not real hard. You should be able to kind of work through it and figure this out. What I would like you to be able to do when we talk about assessment, when we had our meetings last week, we talked a lot about how do you assess yourself, how do you know that you know these things. This is the kind of thing that you should be able to do. So when it says in the objective, describe the structure of atoms, that doesn't mean like just give me a general description of what atoms look like. That means, can you specifically do this? Can you look at a symbol, look at the atomic number, and figure out all the different numbers of subatomic particles? And working through this activity will help you to do that. If it doesn't and you still need help, please let me know so that I can do more. I can meet with you. I can do another video with more like answers and practice problems, whatever would help you to get that. But that's the goal here. All right. Other questions about this stuff? About atoms? Sound good? So for those of you who have done this before, I would encourage you to go a little bit farther. So if you look, let's see if I can grab this. Where's my teams? Sorry, I got too many teams here. If we go back into Module 2 here, you can see that when I put together the objectives, I noted here, if you already know the basics of atomic structure, look at this other thing. So if you already know how to account for protons, neutrons, and electrons, and you kind of understand the basics of that stuff, and you can count those out because you did it in a previous chemistry class, don't just do nothing. Learn something cool and interesting that's new. And one thing you might want to look at is the quantum structure of the atom. So how do we describe the atom based on quantum physics or quantum mechanics, and how is that different from the model that we're seeing so far? So this link here takes you to a chapter of a textbook, which is a nice place to start on that, if that's something that interests you. There are also some great videos and other types of things that you could work on with that. So let me know if you want more references or more to work on with respect to that. But that's part of the point of the more open structure of this course, is if you're encountering something that's easy for you that you've done before, there's no need to waste your time working through it again. Do something else, learn something interesting, and when you fill out your module reflection, account for that instead. Say, I already knew atomic structure, so I read this other stuff that was really interesting, that gave me more detail, more background on atomic structure. All right, so next week, assuming things are working, we'll see, Tuesday and Wednesday, we'll be looking at organic structures, chemical structures, drawing structures in different ways, and it'll be same time, same place. I think we should be fine for Wednesday. Tuesday, we may have to find a different room, but yeah. Thanks, everybody.